Okay, we're going to go over problem 20 from the review. Now these are part of the, this is just bonus. We didn't really have a chance to talk about it much in class, but it sort of ties everything together from the beginning of the year. So I'm happy to walk you through it. So we have a situation where a car is driving and we have these three different rates of speed or velocity that the car is traveling. And we have what we're marking as a velocity and time graph. Sorry, that's a parenthesis there. Time. And so the first bit of travel that the car makes is the first 4 seconds, where it's traveling at this pace of 3t plus 2. So if we want to mark that on the graph, we start at 2 as our y-intercept and go up 3 feet, I think we're traveling for every second. And so we have travel that looks like this. And then the car stops for 3 seconds, which means there's no velocity, 0. So from a point of 4 seconds to 7 seconds, our velocity is 0. And now it's not really clear in the problem where the filled in circle versus the open circle should be, but in order for this to be a function, we know we can only have one output at every input. So I put my open circle at 4 here, put my closed circle up here, but you could have done it the other way around. You could have left this open and filled this in either way. Same thing with 7 seconds. So I'm putting the closed circle here, which means then at 7.001 seconds, the car is traveling at -5 feet per second velocity. So -5, that's a constant rate. That's going to be a flat line at -5. So if it's a filled in circle here, that means I'm going to have an open circle here for the next 5 seconds. So this is the velocity of the car, which looks a bit different than what we're used to seeing, which would probably be distance traveled. But what we learned in this last section is that the distance, and we learned this the very first unit of pre-calc, that the distance can be found by calculating the area under the curve of these graphs. The interesting thing in this one is that we have both positive area and negative area. So if we want to calculate the area under the curve, let's start with this top function here, 3t plus 2. We basically have a rectangle and a triangle. The area of this is 8. The area of this would be 4 times 2 to 14 would be 12. So half of that. 4 times 12 is 48. Half of that is 24. So that's the area of the triangle. So if we look at the whole area under the curve here, we would have 24 plus 8, so 32 feet. The car did not travel any distance when it was stopped, which makes sense. So we had 0 for this amount, and there's no area there, it's just a line. So we have 32 feet plus 0 feet for this part. And then the last bit of travel is when it was traveling at a constant rate, but it was negative. So velocity, remember, is speed and direction. So if we assume it's moving away from the starting point for the beginning, it's moving back toward the starting point for the last 5 seconds. And this is just a rectangle that has an area of from 7 to 12 would be 5, and then down to 5. So it's actually a square that has an area of 25 feet. So then we would add 25 feet to that, but because it's under 0, it's negative 25 feet, going back toward the starting point. And so the question in number 2 is, how far from the start are we? And so if it traveled positive 32 feet from this and negative 25 feet from this function, we add those together and we see that it only ended up 7 feet from where it started. If we're looking at the total distance traveled, then we don't care about what direction it is, so we just take the 32 feet plus the 25 feet and we add them together. Now, one bonus that we have in this is thinking about this in terms of derivatives and antiderivatives. So if we have the function 3t plus 2, one thing we learned in the bonus slides is that the slope function is essentially the velocity, and that's essentially the derivative. So if we think that this function is a derivative function, we can work backwards to figure out what our original function was, which would then give us a distance function, and that would be the antiderivative. So we did not teach how to work the antiderivative here, but I can just show you quickly how that works. And then the other function that was a slope function or a derivative function was f of x equals -5. So I'll show you that one also. So the shortcut power rule that we talked about was that if you have a function, you need to consider what the exponent is here in accordance with the variable t, and to go from the original function to derivative, you would subtract 1 and then take this number and multiply it out front here. Now, if we're going backwards from the derivative back to the antiderivative, which is what we want to get, then we do the opposite. So right now, if we just have t, that means we have t to the first. The opposite of subtracting 1 would be adding 1. So that means that our original function was t squared. And then to figure out what the coefficient was, instead of multiplying over here, we would divide by that. So we had 3, we're going to divide it by 2, we get 1.5 t squared. And then we would consider the same part for the second part of this. So there is no variable here, but remember that anything to the 0 power is 1. So we actually could write it like this. T to the 0 would still be 1. 2 times 1 is still 2. So we're going to do the same process here. If we add 1 to that, that would give us t to the first over here. And then if we divide by that, then we would see that it was 2t. And so that would be our antiderivative, or we could think of it as our original function, and this over here was our derivative. So the antiderivative is just working backwards from the derivative to the original. That's another way to think about it. So that would be a way to calculate distance. So we'll come back to that in a minute. Let's do the antiderivative of f prime x equals -5. Again, we have t to the 0. So if we add 1 back to it, we would have t, and -5 divided by 1 is still -5. So our original function was -5t. Now, if we want to calculate the distance traveled here, we are talking about distance traveled from time 0 to time 4 here. So if we plug in 0 to that function, we get 0 because t squared is 0 to t is 0 when you multiply them. 0 plus 0, 0. And then we're going to plug in 4. 4 squared is 16. 1.5 times 16 is 24. And then 2 times 4 is 8. So we get 32. And then we're going to find the difference between those. So 32 minus 0 is 32. And then for the second function, that was from a time of 7 seconds to a time of 12 seconds. So if we plug 7 into this function, negative 5 times 7 is negative 35. If we plug 12 into this function, negative 5 times 12 is negative 60. And then we find the difference between them. Negative 60 minus negative 35 gives us negative 60 plus 35, which ends up being negative 25, which is the same answers that we got when we calculated the area by finding the space, the shapes, instead of using the derivative and antiderivative. Whoops. I hope that you found that helpful and it wasn't too confusing. It's not something that you have to be able to understand to even be successful in calculus, because it's all going to be hit again. I just thought it was something that was important to show people who are interested, because it sort of ties us together from where we started at the beginning of the year with these velocity and position graphs, and how the derivatives and the antiderivatives and the slope functions and the limits and all this stuff that we've been learning this year kind of ties together into something that you can actually use in real life.